In this video, we will see the proof of convexity of a least square loss function that we have defined for a linear regression problem. So this is the agenda of this particular video. We will see basically two different kind of proofs that are proving that least square loss function is actually a convex function in terms of parameters. So the proofs are not very essential for GATE, but it will strengthen and enhance your understanding regarding the convex functions and how to compute the gradients and how to prove that certain function is convex or not. So those are not essential for GATE, but to get more enhanced clarity, it is good that you understand these concepts. So let us start the video. So before starting this video, it is absolutely essential that you know the results that we have discussed a few lectures back. So I will put the link of that lecture in the pinned comment of this video, also in the description of this video. If you have not watched that lecture, please watch it, because that is a bedrock of this particular lecture, and we will use a certain results that we have obtained on that particular video in this particular lecture. So it is essential that you are aware of the results that we have obtained in that particular video. So if you remember that if there is a certain constant vector y and we are interested in certain function g of input variable x and y, and the function is just a dot product with this particular vector y, where the y is a certain row vector, then the gradient of that particular function g is the transpose of this particular constant vector y. So we have seen this particular result in the earlier lecture. So I will use this particular result and I will refer this as a result 1. Similarly, if the constant vector is a certain column vector and the vector corresponding to the variable x and y is a row vector in the dot product, then the gradient is just the constant vector, which is a y. So I will refer this result as a result 2. Also, how to obtain the gradient of a quadratic functions. So let's say I have two variables x and y, and I obtain certain linear functions using certain matrix A of these variables x and y, and then I just square these linear functions that I have obtained using the function g. So how to obtain the gradient of the g? It is 2 times A transpose A multiplied by the column vector xy. We have seen this result very elaborately, and this is very essential result that we will be using in the future lectures and in this lecture. So it is important that you are fully clear regarding this particular result. So please go through this result if you have not gone through in the earlier lecture, and please be fully comfortable regarding this result, and I will refer this result as a result 3. And similarly, in a special case, if A is a matrix identity, then the gradient of G is just 2 times the column vector xy, and I will refer this result as a result 4. So once you are comfortable with all these results, we can progress in this particular lecture. So please remember the definition of the convex function. So now I am interested in a convexity of a function where inputs are multiple variables. So in general, f function from r to the d to r is a convex if any of these 3 properties are getting satisfied. So first property is analogous to the property that we have seen in the single variable case, that you join a line joining any 2 points in this particular function, then the value in the line will be always higher than the function value. Similarly, you take a tangent at any particular point and you take a certain deviation epsilon, then the value on that tangent will be always lower than the function value at that new point x plus epsilon. And the third property, in terms of single variable case, we have seen that the double differentiation of a function is always greater or equal to 0 at any point x. Now there is a multi-variable case where input is in RD. So the analogous condition is the Hessian. This is called as a Hessian of a function f. We'll see it later also. is always positive semi-definite. So this is a symbol that is being used as a positive semi-definite matrix. So this symbol looks like greater or equal to symbol, but it's not exactly greater or equal to symbol. It is usually symbol referring that certain matrix is a positive semi-definite matrix. So this condition that Hessian of this particular function is a positive semi-definite for all x. So now let's come back to the least square loss function. So we will see the convexity of a least square loss function by two different properties. In particular, in first case we will see the convexity of least square loss function by property 1, which is saying that you take any 2 points and you join a line between those 2 points, then the function value at any point in between that line will be always lower than the value on that line. So this is a property 1, and we will also see the convexity proof by property 3, which is saying that the Hessian of this particular least square loss function is a positive semi-definite. So we will also see that proof in this lecture. So let's revise what was the least square loss function. Here the least square loss function was, if you remember, it was half times sum over I equal to 1 to n w transpose xi minus yi square. So now you have to be very clear what is input, what is output, and what is variable in this particular case. So what is input? Input is xi's. Those are the data point entries that is given as an input. What is output? Output is yi. What is parameter or what is variable? Variable is a w here, right? And that is also parameter. So whatever the input and outputs are there, those are fixed entities once you are given a training data. So input and outputs are fixed. So this entire equation is a function of what? It is a function of w, right? So whatever the variable is, that is the input to the function. So this is entirely the function of w, and xi's and yi's are fixed. So you have to be careful when we have defined the properties of the convex function. If in these properties the x were the variable, but in the least square loss function the variable is w and xi and yi are fixed. So we will see that this function whose input is w is a convex function. So we will see the analogous property for a w, and we have also defined a new form of this particular loss function in terms of matrix. So here the A matrix, if you remember, is of a matrix consisting of a row where each row corresponding to certain data point. In particular, first row corresponds to the data point vector x subscript 1, second row corresponds to data point vector x subscript 2, and likewise. There are n particular data points, so the rows for the matrix A is n, and the columns for this matrix A is d plus 1, since each of these x superscript I is of a d plus 1 dimension, and we are considering the augmented x and augmented w. So this also is a function of what? W. And what are the fixed entities? A and capital Y are fixed. So A is fixed, that is input. Capital Y is just a vector consisting of all ground truths. So that is also fixed, and that is output. The capital Y form is something like this. It is certain column vector where first entry corresponds to y subscript of 1, second entry corresponds to small y subscript of 2, and likewise there are n different entries. So it is a column vector of n rows. And what is the variable in this entire equation? Only the w is variable, and that is a parameter that we are interested in. W is parameter or variable. Okay, so let's start the proof by property 1. So we will show that if we have only single data point, which is x, and the corresponding ground truth value is small y, then the least square loss that we will obtain is a convex. So if we have a multiple data points, in particular if we have n data points, and if we sum for all of them, that is also convex. So we have seen that result, that if the certain function is a convex, then some of that functions are also convex. So we will see only for one term, that is w transpose x minus y whole square. This particular function is a convex, and by the property that we have already seen, that if a certain function is a convex, then you sum similar functions. The sum of convex functions is also a convex function. So this will ultimately prove us that sum over I equal to 1 to n w transpose xi minus yi square, this is a least square loss function when you have a n data points entry. So this is also a convex function. So let's consider this particular square function, which is the inside part of a least square loss function. Now ffw is w transpose x minus y square. Every time you have to be very clear what is input, what is output, and what is parameter. So whatever the parameter is, that is the variable in this particular function. So here w is a variable. Okay, that's why it is a function of w. Fine. And this particular function, what is the domain of this particular function? Again, it is r to the d plus 1, because w is of a d plus 1 dimension. It is certain column vector of d plus 1 dimension, and the final output is in r. So it is an error term. So the codomain is r. Very good. So you fix any capital W subscript 1 and capital W subscript 2 in r to the d plus 1. You fix those points, and we will prove that line joining on these 2 points will be above than the function values on between these 2 points. So let r be a certain random variable. So I am taking certain random variable with the notation r. It is certain random variable which is taking value w1 transpose x minus y. So this is certain real value, right? So I can define a certain random variable which is taking certain real value. That's the definition of the random variable only. So w1 transpose x, since w1 I have fixed, x is also fixed, and y is also fixed. So this is some value in r. So I have defined certain random variable which is taking some real value with the probability alpha. Similarly, this random variable is taking w2 transpose x minus y. This is another real value with the probability 1 minus alpha, right? So I can define a certain random variable like that, right? And I am calling this random variable with the name r. So what will be the expectation of r square random variable? So you square all possible values this random variable is taking, and you do the weighted average. That's what it is taking. So w1 transpose x minus y, that is one value taken by the random variable r, and if I square it, it will become w1 transpose x minus y square, and it is taking that value with the probability alpha. That's the definition of the expectation. You just do the weighted average. So similarly, r is taking w2 transpose x minus y with the probability 1 minus alpha. So r square is taking w2 transpose x minus y square with probability 1 minus alpha. So that term also I have added. So this is expected value of r square. Now if you remember this particular term, what does this particular term represents in terms of our definition? This is just a f value evaluated on a capital W1. That's how we have defined R and F. So this entire term becomes alpha times f of capital W1 plus 1 minus alpha times f of capital W2. Now let's consider what is expectation of R. So expectation of R, you just consider the values taken by R, not R square. So R is taking W1 transpose x minus y with probability alpha, and W2 transpose x minus y with probability 1 minus alpha. So now if I simplify it, alpha and 1 minus alpha, the sum is 1. So you have to be clear that alpha is certain probability. So alpha is 0 less or equal to alpha less or equal to 1. So if I simplify this particular equation, alpha into y and 1 minus alpha into y, the sum is becoming y only, and the first term will become alpha times w1 transpose plus 1 minus alpha times w2 transpose, and this entire row vector will be multiplied by x. So this is just a simplification of the above equation. Now let me square on LHS and RHS both. So LHS will become expectation of r whole square, and RHS is becoming this particular entire equation. Now if you notice this entire equation, this equation corresponds to f evaluated on alpha times capital W1 plus 1 minus alpha times capital W2. That's how we have defined f. So that's what I have written, that expected value of r whole square is just f evaluated on alpha capital W1 plus 1 minus alpha capital W2. So we know that variance of this random variable r is always greater or equal to 0. So the formula for variance is expected value of r square minus expected value of r whole square, which is greater or equal to 0. Now take the expected value of r whole square on RHS side, so we will get this particular equation, which is expected value of r square greater or equal to expected value of r whole square. We have obtained both of this term in terms of f in the earlier slide. So the first term, expected value of r square, is just alpha times f of w1 plus 1 minus alpha times f of w2, and expected value of r whole square is just f of alpha times w1 plus 1 minus alpha times w2. So we will replace both of these quantities in this inequality that we have obtained. So this gives us that alpha times f of w1 plus 1 minus alpha times f of w2 greater or equal to f of alpha times w1 plus 1 minus alpha times w2. And this is just a first property of the convex functions. So what we have proved, for any w1 and w2, for any fixed w1 and w2, and for any alpha in 0 and 1, this inequality gets satisfied. And by definition, the f is just squared error consisting only 1x. So this particular function that we have defined in terms of f, which is w transpose x minus y whole square, is a convex function. Now I consider a similar form of functions, n different functions, and I sum them. Since each of these particular functions are convex function, the sum is also a convex function. So this proves by property 1 that least square loss function for a linear regression is a convex function. Correct? Now let us see the proof by property 3, and for this I require some notion of Hessian of a function, and what do we mean by Hessian of a certain function. So let us start by understanding the Hessian first. The notations that I will be using in this class also, r to the d will be referring some column vector of a dimensions d, and r to the m cross n is referring to a matrix of m rows and n columns. So the Hessian of a matrix is defined as if let's say certain function is there which is taking d input variables, so d variables are there, and it is outputting some real value, then the Hessian is certain d cross d matrix, and the matrix is defined as every entry is a second derivative. So ith row and jth column entry indicates the partial derivation of f with respect to xi first, and partial derivation of f with respect to xj afterwards. This particular matrix is called as a Hessian matrix. Let's the notation wise, this can also be referred as a grad square. So why grad square is, we will see it, it will become very clear soon. But first, let's see through the examples how we can calculate the Hessians. So for a revision, let's try to see, let's say this is a function f, which is taking some input variable, which is some vector x and y, and it is outputting some real value. So del f by del x, everybody please answer. What is the actual answer? A. Rohan is saying A, del f by del x, you consider y as a constant and you differentiate. That is 2x. X is not a constant, so differentiation of x square with respect to x is y is x. So it is 2x, and here y is a constant, but you have to differentiate with respect to x. So ultimately it will become 2x minus y. So the answer is A. You are correct. Then del f by del y again. By the same formulation, we have seen it. You consider x as constant and y as variable. So first term will vanish and it will become 0. Second term will become minus x, because minus x will be considered as constant, and del y by dy will become 1. So the answer is minus x. This is the notations for the f that we have used. If f is a certain function, which is whose domain is r to r square, and it is outputting a value in the codomain r, then del f by del x is also a function. Del f by del y is also a function. Both are function. And the domain is same as r square, and the codomain is also same as r. Same as r. The thing is, if I evaluate del f by del x and del f by del y at certain point, then it will output certain real value. Let's consider this example. I have slightly modified the function, which is I have made it x cube minus xy. Now calculate the gradient of f at certain point xy. So since x and y, we are referring it as a variable, the output will, each of the entry in this particular vector will have a certain function. So del f by del x will become something like 3x square, because x is not a variable. Sorry, x is variable in this case, y is a constant. In a second term, if we consider y is a constant, so the different partial differentiation will become minus y, because del x by del x will become 1. So the first entry will become 3x square minus y, and second entry will become in the first term there is no y, and x is a constant, so it will vanish. And in second term, y is variable and x is constant, so it will be minus x. So some person has also already answered it. It is C. Very good. So 3x square minus y, that is first entry, and second entry is minus x. Very good. Now calculate the Hessian. In Hessian, if you remember the definition, Hessian of x f is certain matrix, and in each matrix we are considering a double derivations, partial derivations 2 times. So first entry will represent del square f by del x square. Second entry will represent del square f by del x del y. In the second row, first entry will represent del square f by del y del x. And in the last row, the second entry will represent del square f by del square y square. Take this function and do the differentiation again. No need to do twice differentiation, because we have already done one time differentiation. That was the same function I did consider. So the first differentiation, del f by del x, I have obtained is a 3x square minus y. Now, if I do a differentiation again with respect to x, what will be the first term? In this term, x is variable. So 3x square will become 6x, and then in second term, y is a constant, so it will become 0. So the first term will become 6x. So that is the first term.
Sir, here the function is different. No? Function is previous one, not the.
Okay. Sorry for that. Let me modify the question bit. I want to keep a function same. Sorry for the slight typo. So let's write this particular matrix. So what is the first term? As I have already calculated, it is 6x. What is the second term? I have already calculated the partial differentiation once with respect to x, that is 3x square minus y. Now I do the differentiation again with respect to y. And what I will get is x is a constant, so first term will vanish and second term is minus 1. Similarly, if I do it again, everybody please answer what is the answer in this particular ABCD. D is the answer. Everybody is getting it. Hopefully, there is no doubt till now. Okay, so let's do one more thing just for the more clarity. If I evaluate this Hessian at 2, 3 point, then what I will get? So here every entry was changing with respect to x. There was x was considered as a variable in this function. But if I evaluate this particular function at certain point, what I will get? Whatever the matrix that you have obtained, you replace x is equal to 2 and y equal to 3 in this. So everybody please tell me what is the answer in this particular question. Right. Any doubt? Anybody thinks that D is still answer? D is not answer because the input is 2, 3, right? C is the answer. Wonderful. So one thing I need to show you is grad square f. If I want to put a domain and codomain here, what will be the domain and codomain? So domain will be R square. I am doing the gradient again, and the domain remains same. The codomain will become I'm sorry, there is slight typo in both in this slide. So ideally, in the gradient, the domain is R square to R square. In the Hessian, the domain is R square and the codomain is R square 2 cross 2. So the codomain is R2 times 2. So how this is changing, you need to understand the pattern. If there is function f, if I do the gradient once, then the domain remains same. So R square is the same domain. Now the codomain will change with respect to number of variables it have. So since it has 2 variables, so codomain will be increased by twice. Sorry, it will be multiplied by twice. Again, you are doing the differentiation. So that is a grad square you are doing, or a Hessian you are doing. Domain remains same. So that is R square. The codomain will multiplied by 2 again. So it will become 2 cross 2. What I'm trying to say is clear to everybody. So f is this. Now you are taking certain input x, y. Okay. Now, when you are taking a gradient, what it will become is certain column vector. And the first entry of this column vector will become a partial derivation of f with respect to x. And the second entry will become partial derivation of f with respect to y. Correct? Now you do the again gradient. If you see in the left hand side, del f by del x is also a function r square to r. Del f by del y is also function r square to r. So doing twice the gradient is nothing but taking a gradient of each of these function or both of these function. So you can see it in that context that if you take a gradient again, I need to take a gradient of both of these function. Earlier it was only one function. Now it has become both of these function, and you can represent it at certain way that you are making it as a row vector now. And this is a gradient of this function del f by del x.
Yes, sir. Yeah. Now understood, sir.
Yes. So if I have to write a gradient of f, so I will write a gradient in gradient, and in the adjacent space, I will write f. If I have to write gradient of del f by del x, in an adjacent space, I will write gradient del f by del x. It's the same notations. Similarly, del f by del y. How I am interpreting it, is it clear?
Yes, sir.
Anybody else has a slightly doubt? Even slight doubt, if they have, they can ask. Okay. Everything is clear, I am assuming, so I'll go further. So I assume a specific form of the function in such a way that the first partial derivation is a linear function. So del f by del xi or del f by del x and del f by del y are linear. In this particular case, were they linear, del f by del x and del f by del y? Here there are del f by del x is not a linear function. Apologies for that. Since there is a second power of x being considered, so it is not a linear function. And original function was x to the power q. But now I'm specifically interested in a function where del f by del x is a linear function. So I'm assuming particular form of linear function. So del f by del xi, it is taking certain value, which is the variables are x subscript of 1, x subscript of 2 up to x subscript of d. And the specific linear form it has is ai1 multiplied by x1, ai2 multiplied by x2, aid multiplied by x2. So I'm assuming this form. If the partial derivation, all the partial derivation have this kind of form, I'm assuming this. I don't know. It will not have every time, but if it has this thing, then can we say something nice about the gradient? So what will be the ith rows of a Hessian matrix? So as our understanding, ith row of a Hessian matrix, take del f by del xi. First differentiate with respect to del x1 again, then differentiate with respect to del x2 again, then differentiate with respect to del xd again. So I have taken this particular equation ai1 x1, ai2 x2 up to aid xd. Now if I differentiate with respect to x1 again, I will get certain constant which is ai1. So first term I will get ai1, second term I will get ai2, and the last term I will get aid. So if all such partial derivation has this property, for all I has this property that first derivation is of a linear form, then I can create certain matrix A where I can put certain coefficients a11, a12, a1d, a21, a22, a2d, ad1, ad2, add, and all of them are entries corresponding to the double partial differentiation. And in terms of linear function, if I want to write, if gradient of f is outputting certain linear function which is a multiplied by certain vector x, so this is what I have assumed also. Please know that if there is a here, if you multiply the x in this form, everybody should know the matrix multiplication rules. So the first entry is x subscript of 1, second entry is x subscript of 2 up till x subscript of d. Now, if I want to see the output will be certain column vector, which is of a dimension d. And the ith entry will represent the equation that we have already considered, ai1, ai multiplied by x1, ai2 multiplied by x2, aid multiplied by xd. So the ith entry will represent that only. And the specific form, if I want to write this gradient function in the matrix form, I can write it as a and then I'm multiplying the column vector x1, x2 up to xd. So this is a if gradient has this form, I'm assuming this. Okay, it need not have always, but I'm assuming this. If gradient has this form, then what can we say about Hessian? So as I have already mentioned, each of these entries, the double derivation, if I try to do, del square f by del xi del x1, del square f by del xi del x2, all of them will yield to the individual entry in the matrix A only. So del square f by del xi del x1 will yield to ai1. So the Hessian matrix, if I try to form it, I will see that grad square f will become a same matrix. Any doubt till now?
Sir, I was thinking of applying that earlier result that you showed us that day. But,
Okay.
So why that can't be applied here or that can't be thought here?
So you can apply it, that result also, but I have specifically mentioned that result in terms of gradient. Now you are computing a Hessian. So every entry, it will be a gradient, and you can apply that result for every entry. The A is certain. So if you try to see, A has certain values. So this particular B, this is certain vector. This is certain vector. Now I'm taking one more vector. So what is variable and what is constant in these cases?
Variable is x1, x2, xd. Yes.
Okay. Now, if I want to do the differentiation, partial different, want to take a gradient of the first entry. So if I want to take a gradient of the first entry, what it will become? So if you see, if you go back to our results were mentioning that if you are multiplying certain coefficient vector as a row vector, then the gradient will become a column vector. But now I'm putting the gradient as a row vector also, only in the Hessian form. So this vector only is a gradient, and that will be as a row vector in the Hessian. So inherently the result is applied. If you don't see it very explicitly, fine, but just see that the two times differentiation, two times partial differentiation are yielding us the coefficient values only. So that's why when we try to form a Hessian matrix, I will get A again. Any doubt till now? Any doubt till this point?
No, sir, clear now.
One more thing I want to mention before we go further is a positive semi-definite matrix. I assume you have, Saloni has covered in the linear algebra classes. For the I will just mention the definition in this particular lecture. And the definition says that if A is a symmetric matrix, I'm assuming certain dimension D cross D, then it is said to be positive semi-definite if for all x, for all vectors x in R to the D, if I do x transpose A times x is greater or equal to 0, then we call it as a positive semi-definite matrix. This is just a definition. So I hope you have covered this in the linear algebra class. We have seen the convex function definition. The third property says that the Hessian or double derivation is positive semi-definite. So this says that the Hessian is positive semi-definite. Once again, I will like to iterate all these conditions are equivalent. So there is bidirectional implication. One implies two, two implies three, three implies one. Everybody implies that those are convex functions. If you prove any one of the property, you are done. Why the need of convex function and why to analyze them separately is if the function is a convex function, then you can compute a gradient, you can equate it to 0. So if you can find certain x star such that a gradient of x star at the f is 0, then x star is a global minima. We have seen this in the last class through certain visualization. We have considered a single variable function. And we have seen that whenever the gradient or whenever the first differentiation is 0, then it is a global minima and there is no need to compute a second derivative test. Any doubt in this statement? So if there is a function, you can think it in this term. In last class we have considered a certain function, which is to be seen as the function specific function was y equal to x square. So if you remember that function, it had a certain graph like this bowl kind of graph, right? Now, if you draw a tangent at every point, what it happens? Here there is a tangent and there is a large negative value for the tangent. Here there is a small negative value. Here there is even small negative value. At certain point it is 0. So at 0 it is 0. Then when it is more than 0, then the tangent or a slope has a more than 0 value. So visually, if I have to convince you, you can think of it in this way that every convex function is some kind of bowl kind of function. And the slope of the tangent is 0 only when it is at the minima. I'm not rigorously proving it because we will deviate from the main goal. But I want to convince you at least visually. Anybody else has a doubt? So let's come to the linear regression problem. So I have written a function as it is in the first step. And in the second step, I have expanded this function. Right? Now, let's say, I'm sorry. Let's compute a gradient. Everybody do let me know how to compute a gradient of each of these terms. The first term is W transpose AW. What is the gradient in this case? Everybody should know that. It is A transpose AW. And how did we arrive that? So it is 2 times A transpose AW. How did we arrive that? It is result 3. What is the gradient of the second term? Everybody should answer. I am taking certain coefficient vector y transpose A, multiplying it as a row, and W is a column vector. So which result is applicable? Result 1 is applicable, correct, Bharat? And as per the result 1, what is the final answer? The transpose of the row vector that you have considered, it is y transpose A transpose, correct? Now take a third term. And what is which result is implying this? Result 1. Everybody is clear. If there is doubt, please unmute and speak. And what about the third term? Third term is W is considered as a row vector. And now I'm taking a gradient of it. So the final output is the coefficient vector, which is already given as a column vector. So it is A transpose Y. Which result is this? This is result 2, right? Any doubt in this? And then what is the gradient of Y transpose Y with respect to W? Last term is not dependent on W. So it is 0. Any doubt in the gradient calculation, anything? So the next thing is just to simplify this. So it is 2 times A transpose AW minus Y. This is the final answer of the gradient. This is clear to everybody? So I will take this gradient. Now this gradient function, I will compute the Hessian also. So everybody do, everybody guide me how to compute the Hessian. First term is 2 times A transpose A W minus Y. You have to compute a Hessian again. Now everybody should guide me. How I can do. So first of all, let me write a gradient in terms of multiple terms. So if there is a bracket, that might be slightly confusing to you. So I will write a gradient in two terms, 2 times A transpose Y. Is this fine? I've just expanded the equation. Now compute the Hessian. Everybody should tell me how to compute it. You are computing Hessian with respect to what? W, right? And what is this? This function is what? The gradient function is what? Linear function in terms of W. Everybody agrees it? A transpose A is linear. Correct? This is a linear function of the W. And you are computing a Hessian. What is the final output of the Hessian? Everybody should tell me. 2 times A transpose A. And what is the gradient of this function? 2 times A transpose Y. If I do again gradient, it will be 0 because it does not depend on W. Any doubt in this? So the final answer is 2 times A transpose A. Okay. Now tell me, this particular matrix that we have obtained, 2 times A transpose A, is it, can I say this function, this matrix is symmetric? Is this symmetric? Obviously it's symmetric because if you do the transpose, you will again get the same matrix. So it is symmetric. Everybody agrees it. I will not even write it. So I have written it, the property symmetric. Tell me, is it a positive semi-definite? Now take any x. For any x, if I do x transpose, whatever the Hessian I have computed it with respect to W, and then again I will do x transpose I will do, then I will again multiply with x. This will give certain real value. What is the Hessian Hessian you have computed? X transpose 2 times A transpose A X. Everybody gets this? Yes. This is L2 norm kind of format. Yes. 2 times X transpose A transpose AX. Correct? Now consider two term. What is the output of this term? What is the output of this term? So AX is what is the need to know the dimension. So A is of a dimension. What is the dimension of A? Everybody tell me. How many rows? N rows and D plus 1 columns, correct? What is the dimension of X? X is how many rows? D plus 1 rows and 1 column, that is column vector. So AX is giving certain row vector, correct? So let me assume that A times X is Y or some other quantity. If it is confusing to you, let me assume there is certain vector Z. So the output of these two multiplication is Z. What is the output of X transpose A transpose? So it is AX transpose itself. So the output is Z transpose. So the final output is 2 times norm Z norm 2 square. And since it is a norm of a function, we can say that it is greater or equal to 0. So I can say that the Hessian I have computed is positive semi-definite. So we will end this video here. In this video, we have seen two different proofs showing that least square loss function that we have defined for a linear regression problem is actually a convex function. You can prove it many other ways. The exact proof is not required for GATE, but it will give you more clarity and you will understand better that how you can compute the gradient and Hessians. So thank you very much for watching this video, and we will meet you in the next video.